Chapter 1: Introduction to Heat Transfer. What is heat transfer? It is the transfer of thermal energy in transit due to the spatial temperature differences. Now, what does transit mean? It means that the energy is being transferred with respect to time. And what causes the transfer of energy is the spatial temperature differences. That means that whenever there is a temperature difference between any 2 points, there will be a transfer of heat between the 2 points. Now, before moving forward, we need to know what is the difference between heat transfer and thermodynamics. So, almost all of you have completed the course on thermodynamics and you are well aware of what the first law of thermodynamics is. So the equation of first law of thermodynamics states that del Q is equal to del U plus del W. And what does it tell us? It tells us how much of heat is being transferred. It tells us what is the final state of the system. And it tells us how much work was done. So the first law tells us how much heat was transferred into or out of the system, what is the final state of the system, and how much work was done by the system or on the system. But how is heat transfer different from thermodynamics? So in this course, we will find the rate at which heat is being transferred. For example, how much time will it take for your tea to boil? How long will it take to cool your rooms during the summertime? The second thing that we'll learn is the mode of heat transfer. There are three modes of heat transfer. First is conduction, second is convection, and the third is radiation. We'll be learning about each mode in detail in the upcoming chapters. And the third information that we'll learn in this course is how to find the temperature distribution in any given system. So for example, you want to find out how does the temperature of water vary as we go down the surface of the lake. So for example, during the winter time, the surface of the lake will be frozen, but the bottom of the lake will still have liquid water and will be much warmer than its surface. So let's go back to the first law of thermodynamics, which is nothing but the conservation of energy. Now the equation for the first law is del Q equals to del U plus del W. Now in thermo, if you know the pressure and temperature of the air in a piston cylinder assembly, you can find the delta U using the tables. For the work done, if you know what uh, process the system is going through, if it's a polytropic process, if it's a constant pressure process, you have different equations and you can calculate how much work is done. But you don't have any specific equation to calculate del Q. Del Q is either given, you will be given how much heat is being transferred or how much energy is being transferred, or you'll calculate the del U and del W to find out the del Q. So in this particular course, we will be concentrating on how to find del Q. So moving forward, let's rewrite this equation as Q net equals to delta EST, which is the energy stored in the system, plus W net, which is the net work done. Uh, if we take the work on the other side and rewrite the same equation, it will be energy stored in the system, or the change in the energy stored in the system is the net energy going in or going out of the system minus the work done. Now, if there's no work done, if there is no work done on the system, we can ignore this term, and there will only be transfer of thermal energy into or out of the system. So this will make our first law of thermodynamics as the energy stored in the system is equal to the net thermal energy going into or out of the system. We can also write this as Q in to the system minus Q out of the system plus Q gen, which is if there is any source that is generating heat or thermal energy in the system, we will consider that as well. Now, an important thing to remember is the dimension of Q. So the dimension of Q, and uh, to so if you see any square brackets around a quantity during this course, that means that we are looking for the dimensions or unit of that quantity. So the dimensions or unit for the thermal energy transfer is joules. It's the unit of energy, and you must remember this for the remainder of the course. Okay, so let's look at how energy stored in the system changes with time, or the rate of change of energy stored with time. For that, what we'll do is we'll take the derivative of the energy equation with respect to time, which will be the d of dt of EST, that is the energy stored in the system, and the time derivative of Qn with respect to time, the time derivative of uh, Q out, and the time derivative of Q generated. This will give us EST dot. So the dot here means the rate of change of that particular quantity with respect to time, plus Q gen dot, and this can also be written as little q's. So during this course, wherever you see little q's, that will mean that you're looking at the uh, rate of heat transfer, or the heat being transferred with respect to time, and Q gen. So this basically is the energy conservation of energy equation that we have and that we will be using in this course. Now the dimension of the Q dot, or let's say the little q, the units for this will be joules per second. That's because it's with respect to time, or watts. So these are the units for the rate of heat transfer, which we will be using in our heat transfer course. So to summarize, the energy balance equation is E dot St, in the rate of energy stored in the system, equals to Q in minus Q out. That's the transport of energy across the controlled volume, and we'll see what controlled volume is in the next few moments, plus the spontaneous energy that's being generated into the system. So this energy generation can be because of several reasons, which we will look through examples in the next few videos. But we also saw that the units for Q were watts, but some other notations that you might come across are heat flux. So heat flux is the transfer of energy, or the rate of transfer of energy per unit area. So rate per unit area, and the notation for heat flux will be Q double prime, and the units for heat flux, because it is per unit area, it will be watt per meter square. So this is also very important, and you will also come across something called as the energy generation, or energy generated per unit volume. In the textbook it is denoted as Q dot, but we can also denote this as Q triple prime, and the units for this will be watt per meter cube. So these are some units that you need to keep in mind for the rest of the course. So let's see how the energy balance equation looks like across a controlled volume. Now, something to note is that if you're working in a 3D space, you will have a controlled volume, but if you're working in a 2D space, you will have a controlled surface. Now, let's say our energy transport equation or energy balance equation is EST Q in minus Q out plus Q gen. Now, how will this look across a controlled volume? Say we have an arbitrary controlled volume which looks like this, and there's Q in going into the system, there's Q going out of the system, and there's some source term which is generating a Q gen amount of energy, which is eventually stored as E dot ST into the system. Now, and this is your control volume. Now let's rewrite this equation as EST equals Q in plus Q gen minus Q out. Now let's say if your Q in plus Q gen, if your Q in plus Q gen is greater than Q out, this will mean that you are storing energy into the system. But if your Q in plus Q gen is less than Q out, that means you are removing energy from the system. So in this case your right hand side will be positive. In this case your right hand side will be negative. Now another thing to remember is, if you have a controlled volume or a controlled surface, and if you're looking at heat flux, say instead of Q in, you are looking at the heat flux across the control surface, say heat flux in or heat flux out, your area that you consider must always be perpendicular must always be perpendicular to the direction of heat flow. And we will look at this with the help of a few examples in the upcoming few slides or in the next video. But this is a very important thing to note, that your area, if you're considering heat flux, will always be perpendicular uh, to the direction of heat flow. So moving on to the modes of heat transfer. So as we looked earlier, there are three modes of heat transfer: conduction, convection, and radiation. So in this slide, we'll look at what conduction means. So conduction is nothing but the transfer of energy across a system boundary due to temperature differences. Now this transfer of energy takes place through collisions between molecules. It does not require any bulk motion of matter, and the collisions may occur due to intermolecular attraction. So these intermolecular attraction may be a vibration. So say a particle is vibrating about itself and then it collides with its surrounding particles, hence transferring energy. Uh, the molecules can translate about in a lattice of solid or a fluid and transfer energy by collision to surrounding particles or molecules, or they may transfer energy by rotating about themselves. So these are the three ways in which uh, the energy can be transferred by collision, and this mode is called conduction. So basically, let's say you have a pipe or a solid plate which is rectangular, and one end of the plate is at higher temperature T1, the other end of the plate is at a lower temperature T2. T1 is greater than T2. This means that uh, your one end of the plate has higher energy, one end of the plate has higher energy than the other end of the plate, and energy tends to diffuse from higher to a lower temperature because it wants to level out and create a balance within the system. And this happens due to conduction when you have a solid, or it happens in a liquid as well. So let's look at the heat flux or the heat rate due to conduction. So the heat rate or the heat flux due to conduction can be computed or can be calculated using the Fourier's law. And to understand what Fourier's law is, let's consider a simple solid object. In this case, it's a simple rectangle. Let's say this location here is x1 and this edge here is x2, and positive x is in this direction. Let's say the surface on the left is at a temperature T1 and the surface on the right is at a temperature T2, and we assume that T1 is greater than T2. This means that the left surface is hotter than the right surface. So obviously heat will flow from a high temperature to a lower temperature. So the direction of heat flux will be in the positive x direction. And the temperature distribution within the object will look something like this. So the left surface will be at a higher temperature, the right surface will be at a lower temperature, and the temperature within the body will gradually decrease. Now, this is an example of a one-dimensional heat flux. And please note that I'm using heat flux. So we are looking at heat flux, which is heat being transferred per unit area. So in this particular scenario, our area here will be the area perpendicular to the direction of heat flow. So this will be the area of significance. Now, what is Fourier's law? Fourier's law states that your heat flux in the x direction is proportional to del T by del X. Or if you remove the proportionality constant, your heat flux equals to minus kappa times dt by dx, where kappa is the thermal conductivity. It's a material property, and the value of thermal conductivity for different material, for example iron or aluminium, can be found out from the appendix of your textbook. And you will have different values for at different temperatures for different materials. And the value of kappa here is, or the thermal conductivity here, is found out experimentally. So the next question that we need to answer is, what are the units of kappa? So what are the units of kappa? So our heat flux on the left hand side is in watt per meter square. Temperature here is in Kelvin, and X here is in meter. So effectively our kappa will have the dimensions or the units of watt per meter Kelvin. So this is another important thing. And remember, this is K and this is kappa. This right here is Kelvin, and this right here is kappa, which is the thermal conductivity. So this equation right here is if you have heat flux or heat flowing in one dimension. So in this case our in one direction. In this case our direction was x direction. But what if we have heat flowing in three dimensions? So if you want to the equation for heat flux in all three directions, so in three dimensions your heat flux will be minus kappa times del of temperature. Moving on to the next mode of heat transfer, that is convection. So what is convection? Convection is the energy transport across a system boundary due to a temperature difference by a combination of intermolecular interaction and bulk transport. So for conduction, we just had the intermolecular interactions responsible for heat transfer, but for convection, the intermolecular interaction and the bulk transport both occur simultaneously. Now, how do we find the heat transfer due to convection? We use the Newton's law of cooling. Now, let's take an example of a hot plate. So let's say you have a hot plate which is at a temperature of Ts, and the air surrounding it is at a temperature of T infinity, and you have air blowing over it in this direction. So as Ts is greater than T infinity, there will be heat being transferred from the plate to the surrounding. And in that case, your convective heat transfer, or the heat flux due to convection will be H, which is the heat transfer coefficient, times Ts, that's the surface temperature, minus T infinity, which is the temperature of the surrounding. Now, what will be the heat transfer rate due to convection? It will be the heat flux due to convection multiplied by the area, which is H times A. Now, A here is the area of the surface, so it will be this particular area of the plate, because the heat is being transferred from the surface of the plate to the surrounding, times Ts minus T infinity. And the heat transfer coefficient here will have the units watt per meter square Kelvin. Okay, moving on to the third mode of heat transfer, which is radiation. So what is radiation? Radiation is the transfer of heat through electromagnetic radiations that arise due to temperature of the body. So notice the difference between the definition of radiation and convection or conduction. For convection or conduction, we needed a temperature difference between 2 points or within a system. But for radiation, if if a body has a certain temperature, it will emit radiations. Uh, it will emit electromagnetic radiations due to the temperature. And radiation does not require any material or matter for heat transfer. So let's understand radiation with a simple example. So let's say we have a arbitrary surface or a flat plate like we had for convection. This flat plate is at a temperature Ts, the surface temperature of the plate is Ts, and the surrounding of this plate is at a temperature of T surrounding. Due to the temperature Ts, the plate or the arbitrary surface that we have will emit a radiation E, and because of the surrounding temperature, the plate will receive an irradiation of G. So E here is the emission or radiation out, and G here is irradiation or radiation in. So let's define each of them. So let's take emissivity first. So let's take emission first. So let's see what how we can calculate emission. So your radiation out will be epsilon times sigma into Ts to the power 4. So your emission or radiation out is proportional to the fourth power of temperature. Now what is E? E is a non-dimensional quantity, and it's called emissivity. It's usually 1 for a black body. Sigma is a constant. It's called the Stephen Boltzmann constant, and the value for sigma is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4, and Ts is the absolute temperature of the surface. So by absolute, I mean the temperature has to be in Kelvin. Let's look at irradiation now. So your irradiation G, which is the radiation coming in to the system or into the surface, is alpha times sigma into T surrounding to the power 4. Now alpha here is the absorptivity of the surface, and for gray bodies your epsilon, that's the emissivity, will be equal to your alpha, which is the absorptivity. So if we take the net heat transfer due to radiation, our equation will be net will be epsilon sigma times Ts to the power 4 minus alpha sigma times T surrounding to the power 4. Now if we assume alpha is equal to epsilon, our equation becomes epsilon sigma into Ts to the power 4 minus T surrounding to the power 4, and that's our net heat flux due to radiation. Now a thing to note is that the value of epsilon or alpha will always be between 0 and 1. So in the next few chapters we will be learning in detail about conduction, about convection and radiation. So see you in the next video.